Hi class, welcome to Anatomy and Physiology 1, Bio 14. In this discussion, we're going to focus on the physiology of the muscular system, specifically the length tension relationship of muscles. So how much force can we generate with the muscle based on how stretched out or how contracted the muscle is? So let's think back and review. The structural and functional unit of a skeletal muscle is going to be the sarcomere. And within that sarcomere, we are going to have thick and thin filaments. So if we're looking at those thick and thin filaments, if our muscle has lots of overlap between the thick and thin filaments, there's not that much more room that we can overlap them. The thick filaments of the sarcomere are just going to up against the Z discs of the sarcomere. However, if our muscles are stretched out too far before we try to contract our muscles, we don't have enough overlap between the thick and thin filaments to initiate a cross-bridge cycle. Not that many myosin and actin heads will be myosin heads and actin subunits will interact with each other. So we have very minimal cross-bridge formation and our muscles are weak. So we can generate the most force when there's just a medium amount of overlap between our thick and thin filaments, our thick and thin myofilaments. And in this situation, we're going to be able to have room to contract and have enough overlap to initiate enough cross bridges between myosin and actin. So what we find is that the best or the way to get the most strength out of your muscles is to have them partially contracted, not all the way contracted, not all the way stretched out, somewhere in between. And we find that our nervous system is going to have partial contraction, aka muscle tones, maintained of nearly all of muscles in our body so that we're ready to go when we need them. So this is a figure reiterating what I just talked about. If the thick and thin filaments are overlapping by a lot, the thick filament right here, that myosin, will butt up directly against the Z disc. There's not that much more room to contract. On the other hand, on the other end of the spectrum, if our muscles are stretched out too far, there's not enough overlap between the thick and thin filaments, and we can't have enough cross bridges. So we need just a little bit of overlap. And then we can have optimum tension, optimum force generated by the contraction of our skeletal muscle fibers. Now, after somebody passes away, they're going to have rigor mortis set in. Rigor mortis is when the skeletal muscles become very stiff. And it happens because as the skeletal muscle fiber starts to deteriorate, the sarcoplasmic reticulum, the SR, releases calcium ions. And this is due to a lack of ATP. As we start to lose ATP from our skeleton or from our skeletal muscle fibers, the calcium ions can no longer be maintained within the sarcoplasmic reticulum. They start to ooze out into the cytoplasm of the muscle cell, also known as the sarcoplasm or cytosol. And then that calcium activates tropomyosin moves out of the way, and we have actin-myosin cross-bridging occurring. And our muscle will then have thick and thin filaments stick together very tightly. However, we don't have a lot of ATP in this situation because the ATP that maintained the calcium in the sarcoplasmic reticulum has been all used up. So we can initiate a cross bridge between actin and myosin, but we cannot break the cross bridge between actin and myosin. So it's not so much that our muscles contract. It's mostly that our muscles have actin and myosin fused together, and we can't unfuse them because we're lacking that all-important ATP. And our fibers are going to remain fused until the myofilaments themselves start to decay. How long does this decomposition process take? Well, it's going to take about 48 to 60 hours. At first, it's going to start initiating at about 12 hours post-mortem, assuming that we're above freezing temperatures outside. Obviously, if it's colder, this process is elongated. If it's warmer, this process is accelerated. And then we'll have rigor mortis peak at about 12 hours after death. And then 48 to 60 hours post-mortem, depending on the temperature outside, we'll have rigor mortis go away. For me in particular, I grew up in the boondocks. You know, there's a lot of hicks, a lot of deer hunting. And this one gentleman that I just loved, he was a fantastic guy. He would go deer hunting and he would swear to me that he would need to take his deer and hang them up in his shed for 4 to 5 days so that they would be post rigor mortis. And the reason he liked to hang his deer carcasses up in the shed for 4 to 5 days so they could be post rigor mortis is because the meat was extra tender, because they had partial decomposition of the myofilaments within the skeletal muscle fibers. So let's talk about analyzing our muscle twitch relationship over time. This is known as a myogram. And we can have time on our x-axis and muscle tension on the y-axis. So we have our independent variable of time, dependent variable of muscle tension. And a myogram is a way of analyzing the tension on a muscle over a period of time. We find that the threshold voltage of our skeletal muscle fiber, it's just whatever that minimum voltage is, that minimum change in voltage that we need to initiate the excitation contraction coupling, or to initiate the action potential across the sarcolemma of the skeletal muscle fiber, enough at least to produce a twitch. And it takes time for that electrical signal to travel across the surface of the muscle cell, and then for the calcium ions to move through the inside of the cell, and then for the actin and myosin to go through the cross-bridge cycles. So there's going to be a little bit of a lag period before we have a little bit of a twitch, which is just a quick contraction and then relaxation of our muscle when the stimulus is at or higher than threshold. So let's talk about the latent period. That latent period is a very brief period of time that where we physically are going to have action potentials traveling across the surface of the cell, on the T-tubules, calcium ions being released from the sarcoplasmic reticulum and initiating the excitation contraction phase. So it's usually a couple milliseconds. During contraction phase, we are going to have the cross-bridge cycles occurring. So we're going to increase the amount of overlap between actin and myosin. And then finally, during the relaxation phase, the relaxation phase is a little bit gentler because it's not going to be as actively pursued by our body. We don't need to relax our muscles very quickly. It's contracting our muscles, being able to run away. That's more important to do from a physiological perspective. So our sarcoplasmic reticulum slowly will absorb calcium ions against its concentration gradient using ATP. That causes myosin and actin to be released from each other, and then the muscle tension decreases. And then we're going to have a decrease in tension. So how long this twitch takes varies. If we have fast twitch fibers, we're going to have 7 milliseconds. If we have slow twitch endurance fibers, we're looking at closer to 100 milliseconds. So as we're looking at our muscles, if we have a sub-threshold stimulus or a stimulus that's not up to the threshold voltage, there's no contraction. But once our stimulus gets above threshold voltages, so like these stimuli over here, we're then going to have contraction. We're going to reach threshold. So we can find that how can I say this? We're going to find that once we have those higher stimuli, those higher depolarizations of the membrane, we're going to be able to initiate twitches. And what we find is that different twitches are going to vary in strength. One of the things is the muscle starting length. Is the muscle fully extended? Is the muscle fully contracted? Or is it partially contracted? Another thing to figure out that is a factor is going to be fatigue. What is the metabolic state of the muscle? Is there a lot of oxygen present on the inside of the muscle? Or is there a high or low ATP concentration? We also find that warming up is going to make it so the enzymes work more efficiently within our muscles. There is physiological advantage to warming up before athletic competitions. And then finally, the hydration level. If we don't have enough water in our bodies, the cytosol of the skeletal muscle fibers are going to be too viscous. Ben, I'm making a recording right now. Could you please wait? And if that cytosol is too viscous, that increases the amount of time it takes for calcium ions to diffuse from the sarcoplasmic reticulum to the actin and myosin. Something else that's going to influence the strength of contraction is going to be the voltage. So if we have a higher voltage that's farther above threshold, the higher that voltage is above threshold, the more nerve fibers we're going to excite. So if it's below threshold, 0 nerve fibers are excited. And then if it's far, far above threshold, we have lots and lots of nerve fibers excited. And as more and more nerve fibers are excited, we are going to have increasing amounts of contraction. Another way to think about this is the higher the voltage, the more motor units we recruit. And that means that we are going to have this gradient. As we increase the voltage, we can increase the strength of contraction until we get to the maximum strength of contraction. And eventually, it doesn't matter if we have a stronger stimulus. We can't recruit any more skeletal muscle fibers, and we can't have any more increase in the strength of contraction. Something else that influences the strength of skeletal muscle fiber contraction is going to be the frequency of the stimulus. If we have one stimulus and then a long period of time followed by another stimulus, the muscle can contract a little bit and then it relaxes. Then it'll contract a little bit and then it relaxes. So those low frequency stimuli produce weak identical twitches. But if we increase the frequency of the stimulus, this is known as incompleteness or temporal summation. If we have high frequencies, the muscle cannot relax all the way. So instead of allowing for the muscle to twitch, contracts, and then instead of letting it relax all the way, it starts to contract again, and then it'll start to relax a little bit, and then another stimulus hits, and it contracts a little bit more, and we end up with this stair-stepping as we increase the strength of contraction. Every once in a while, we're going to have a very unnaturally high stimulus frequency. And to give you some reference points here, high frequencies for our bodies include about 20 stimuli per second or 20 voltage changes per second. Unnaturally high frequencies can include something like getting electrocuted by wall voltage. In the United States, most outlets in your house are going to alternate at 60 hertz or 20 stimuli per second. And this is one of the reasons why when a lot of people are getting electrocuted in their houses, they just freeze and go rigid. They have that complete fused tetanus. Their muscles lock up on themselves. I remember very specifically my sophomore year of college. I was active in the chemistry club at University of Minnesota Duluth, and we were practicing a demonstration. And one of my classmates accidentally started to electrocute herself. And we never really even noticed that she was being electrocuted because she grabbed the electrodes and immediately all the muscles in her body seized up and she went stiff and fell against the wall. And because she was stiff, she was propped up against the wall. And it took her about 45 seconds until she tipped over. And as she tipped over, the electrodes that she was hanging onto, because she couldn't let go, got yanked out of the variac and she stopped electrocuting herself. Something that left a very strong impression on me as a young person. As we're looking at muscles that can contract, we can have an isometric contraction, iso meaning same, metric meaning length, so the same length contractions. So what's an example of an isometric contraction? This is when you're trying to push something that you're not strong enough to move. Or we're going to have our muscle contract, not move. So we can have postural muscles that hold your head up, that hold your torso up. They're contracting, but they aren't moving. This is a good example of isometric contraction. Or if you ever had to do wall sits, that's another good example of isometric contractions. We also can have isotonic for same tension contractions. And an isotonic contraction is when we have the same kind of force being generated the entire time it's being contracted. Typically, isotonic contractions are going to have a change in length with no change in tension. Every once in a while, you can have an isometric and an isotonic contraction at the same time. That's an exception to the rule. Usually, it's one or the other. So, an isotonic contraction is just picking up anything, moving anything. If there's any kind of movement, it's an isotonic contraction. And then we can also have eccentric contraction. And an eccentric contraction is a special kind of isotonic contraction where we are going to have the muscle elongating while the muscle is contraction. The best example of that is slowly lowering a weight, having something heavy and lowering it to the ground gently. And if you've ever tried to do that, it's really, really hard. eccentric contractions are among some of the most difficult contractions. But if you're into powerlifting or lifting weights, eccentric contractions in a weight room setting are what give you the most bang for your buck. So here we're going to have an isometric contraction. Maybe this individual is holding the weight steady. This person has just chosen not to move the weight, or maybe it's too heavy for them to move. Then, oh, check it out. They powered up. They're able to move the weight. The muscle itself is getting shorter. This is an isotonic contraction, specifically an isotonic concentric contraction. And then when we have an eccentric contraction, an isotonic eccentric contraction, there's still going to be the same tension, and this individual is going to be slowly lowering the dumbbell while the muscle is elongating with constant tension. And as we're looking at isometric versus isotonic, there's going to be a little bit of overlap between the two. Whenever a muscle is just starting to contract, the muscle is going to have an increase in tension. The muscle is not going to shorten. And this is for a very brief period of time, known as the isometric phase of contraction, when we start to contract the muscle, but it hasn't actually changed length yet. However, in a short period of time, usually tension is going to overcome the resistance of the load, unless you're trying to pick up your car and you're not strong enough to pick up your car. And in those situations, tension will stop increasing, and we're going to have muscles begin to shorten, assuming you're strong enough to move whatever the heck it is you're trying to move. And then you're going to be in the isotonic phase, the same tension phase. And that's all we have for this recording. I just want to encourage you, if you are struggling through the assigned physio exercise, these topics are of key importance to helping you understand your PhysioX homework assignment on excitations and contractions of skeletal muscle fibers. As always, if you have any questions, please feel free to shoot me an email or post them on the class discussion board, and happy studies.